Hello everyone, my name's Iman. Welcome back to my YouTube channel. Last time we looked at weak acids and weak bases in water, and we also discussed simple buffers. Today we're going to put those pieces together and look at neutralization reactions. Neutralization reactions happen between acids and bases where they exchange a proton and leave behind a salt and often water. We're also going to cover titrations in this lecture. Before we start any of that, I do want to quickly remind you the rules for writing net ionic equations. And then we're going to go through 4 cases where we ultimately want to write the net ionic equation for. To write the net ionic equation, the first step is you want to write the balanced molecular equation. Then in step 2, you're going to expand anything that is a strong electrolyte into ions in the total ionic equation. That means strong acids, strong bases, and soluble ionic salts split into their ions. But weak acids and weak bases, they do not split. We leave them written as is. Step 3, you're going to cancel spectator ions. These are the species that are going to appear unchanged on both sides. Whatever remains is the chemistry, and that is the net ionic equation. In addition, just a friendly reminder, in water, hydrogen ions, H+, is really hydronium, H3O, with a +1 charge. But in net ionic form, we often write H+ as a shorthand. With that, let's begin with our first case, the reaction between a strong acid with a strong base. Let's use hydrochloric acid with sodium hydroxide as our example when discussing this. In the molecular equation, we write hydrochloric acid, HCl, reacts with sodium hydroxide, NaOH, to make sodium chloride, NaCl, and water, H2O. In the total ionic equation, HCl and sodium hydroxide, they both split completely. So we write hydrogen ions, chloride ions, sodium cation, and our hydroxide ions on the left. And then on the right, sodium chloride is a soluble salt, so it completely dissociates. We write it as sodium cations plus chloride ions and water on that right side. You'll notice very quickly, chloride and sodium, they appear on both sides unchanged. So they are spectator ions, and we can go ahead and cancel them. The net ionic equation is then simply hydrogen ions plus hydroxide ions form water. And the takeaway is that when both partners are strong, when you have a strong acid reacting with a strong base, only the hydrogen ions and the hydroxide ions participate, and everything else is a spectator ion, and the salt solution that remains is going to be neutral. Now let's move to a strong acid with a weak base. We'll start with an example that actually involves a neutral weak base like ammonia. So in the molecular equation, we're going to have ammonia reacting with hydrochloric acid, which is a strong acid. Hydrochloric acid reacts with ammonia to give ammonium chloride. In the total ionic equation, that strong acid obviously splits into hydrogen and chloride ions. But ammonia stays as NH3 because it is weak. Then you'll notice chloride ions appear on both sides unchanged, so they cancel out because they are spectator ions. The net ionic equation then reduces to hydrogen ions plus ammonia gives us ammonium. So, in other words, the hydrogen ion plus the base gives the conjugate acid. So we can write this in the general form, H plus the base gives us the conjugate acid, BH, with a +1 charge. The message here is that a strong acid protonates a neutral weak base to make the conjugate acid, and the solutions containing the conjugate acid tend to be acidic. Now, sometimes the weak base arrives as an anion from a salt, which is the second version of this same case. So for this example, let's think of a strong acid like hydroiodic acid meeting sodium formate. In the molecular equation, the products are formic acid and sodium iodide. In the total ionic equation, the strong acid and the soluble salt split, but the weak acid that forms does not. And then you'll recognize sodium and iodide, they appear on both sides. They cancel out because they are spectator ions. The net ionic equation then becomes hydrogen ion plus the conjugate base produces the weak acid. So we can write this as H plus our conjugate base, A with a -1 charge, that produces the weak acid, HA. And the takeaway here is identical. A strong acid converts a weak base, whether neutral or anionic, into its conjugate acid, and so the mixture is going to lean acidic. Our third case is a weak acid with a strong base. So here we'll take a look at hypochlorous acid with sodium hydroxide as our reference reaction. In the molecular equation, hypochlorous acid reacts with sodium hydroxide to form sodium hypochlorite and water. In the total ionic equation, the strong base splits to sodium and hydroxide, while the weak acid remains as is. Sodium is going to cancel on both sides since it's a spectator ion. So then, the net ionic equation we get, the form of the net ionic equation is HA, our weak acid, plus hydroxide ions. Those react to give us the conjugate base, A with a -1 charge, plus water. And the solution here is going to lean basic. The last case is a weak acid with a weak base. Here, neither partner is expanded in the total ionic equation because they're both weak. And there's going to be no strong spectator ions to cancel. And because both are weak, this reaction is very much reversible, and the position of equilibrium depends on the relative strengths of the weak acid and the weak base. If the base is stronger than the acid, the mixture is going to lean basic. And if the acid is stronger than the base, then it's going to lean acidic. But the takeaway is that weak with weak does not automatically neutralize, and the direction and the pH, they really depend on the stronger conjugate pair, which is a case-by-case sort of thing. And we are not going to focus on this case very much in this course, but I still wanted to introduce it. Since we now understand how acids and bases neutralize each other to make a salt and often water, we can move into titrations. A titration is simply a controlled way to run that same neutralization while we watch the pH respond in real time, so that we can measure something about the unknown solution. Let's begin with the basic principle. In an acid-base titration, you deliver a solution of known concentration into a solution of unknown concentration until the neutralization reaction has gone to completion. You track how the pH changes as the known solution is added, and that changing pH lets you pinpoint the key moment in the reaction. What about the setup? The tall tube with a stopcock is a burette. It dispenses precise volumes that you can read from the scale. The liquid in the burette is the titrant. Its concentration is known accurately. And in this chapter, it's usually a strong acid or a strong base so that the proton transfer step is clean and fast. The liquid in the flask is the analyte. This is the solution you start with, and it is the one whose concentration or equilibrium constant you want to determine. And as the titrant drips in, you want to swirl the flask so that the reaction keeps up with each addition. Now, there are two special moments to keep in mind regarding titrations. The equivalence point is the chemical point where the stoichiometric amounts of acid and base have reacted. So for a simple monoprotic system, that means the moles of acid that have been neutralized, they equal the moles of base that have been supplied. Then the endpoint is the observable signal that tells you to stop, typically through an indicator's color change or the sudden jump on a pH meter that you're using to monitor the pH. In a well-designed titration, that endpoint coincides as closely as possible with the equivalence point. In addition, I want to pause here and I want to talk about dilutions. For a monoprotic strong acid reacting with a monoprotic strong base, the mole ratio at equivalence is 1:1. That means the moles of hydrogen ions delivered equals the moles of hydroxide ions delivered. If M is molarity and V is volume, the relationship at equivalence is M1V1 equals M2V2, where the subscripts here are initial and final state. Or you could write it as M concentrated V concentrated equals M diluted V diluted. If the stoichiometric ratio is not 1:1, then you can account for this by adding moles on each side of this equality. So it can be N1 M1 V1 equals M2 M2 V2, where N is the number of acidic protons or hydroxides per formula unit. This is really important to understand, and it can make certain calculations super easy. So let's do a quick example to demonstrate the use of this equation. The example says 40 milliliters of 0.5 molar hydrochloric acid are required to neutralize 20 milliliters of a sodium hydroxide solution. What is the concentration of the sodium hydroxide? To solve this problem, we use the 1:1 stoichiometry for a monoprotic strong acid reacting with a monobasic strong base. So we can write M1V1 equals M2V2. You can write this as M acid V acid equals M base V base. Whatever little subscript helps you signal what you're trying to calculate from what you know. So we have 0.5 molar HCl solution. That's the acid. We have 40 milliliters of it, and that is what's required to neutralize 20 milliliters of sodium hydroxide, which is the base. Let me repeat that. We have 0.5 molar hydrochloric acid solution, and 40 milliliters of it are required to neutralize 20 milliliters of sodium hydroxide. If we go ahead and plug things in, we get 0.5 molar times 40 milliliters. That's the molarity and the volume of the acid multiplied together. That's equal to the molarity of the base times 20 milliliters, which is the volume of the base. We can rearrange this to solve for the molarity of sodium hydroxide. And the thing here is we can actually keep the volumes in milliliters because they're going to cancel in the ratio. So I'm going to divide both sides by 20 milliliters so I can isolate the unknown. The molarity or the concentration of sodium hydroxide is going to be equal to 0.5 times 40 divided by 20, and that is equal to 1 molar. So that is our answer. With that foundation in place, let's look closely at the titration of a strong acid with a strong base to get us started. To orient ourselves on any acid-base titration curve that we're going to see here, the vertical axis is pH, and the horizontal axis is the cumulative volume of titrant delivered from the burette. You begin at the initial pH of the analyte before any titrant is added. And then as you add the titrant, the curve records how the pH responds. The steep, almost vertical section in the middle, that marks the equivalence region. The midpoint of that rise is the equivalence point where stoichiometric amounts of acid and base have reacted. The pH at that point depends on the strengths of the reacting acid and base. After you pass the equivalence point, the curve levels off into a new plateau that reflects the pH set by the excess titrant. Now that we've discussed that, let's focus on our case of a strong acid reacting with a strong base. So think of hydrochloric acid in the flask and sodium hydroxide in the burette. Because both are strong electrolytes, they dissociate completely. So the only chemistry is hydrogen ion reacting with hydroxide ion to make water. And that is exactly the net ionic equation we wrote earlier for this pairing. The curve, therefore, breaks cleanly into three regions that you can analyze with simple stoichiometry. Before the equivalence point, the solution contains excess hydrogen ions from the strong acid. Then each drop of hydroxide you add neutralizes an equal amount of hydrogen ion. So the pH, it starts low and then it rises gradually because acid is still present and the total volume is increasing. At the equivalence point, the moles of hydrogen ion delivered by the acid exactly equals the moles of hydroxide delivered by the base. So for a monoprotic acid and a monobasic base, that is a 1-to-1 mole ratio, and the solution at equivalence is simply a neutral salt dissolved in water. At room temperature, this mixture is effectively neutral, so the pH at equivalence is about 7. On the curve, this appears at the midpoint of that vertical rise. You can have indicators that change color near pH 7. Those work really well here for the titration of a strong acid and strong base because their transition range really straddles that sharp jump. Beyond the equivalence point, you're going to have added more hydroxide than there was acid to consume it. So then the excess hydroxide controls the pH and the curve flattens into a high pH plateau. So in summary, the chemistry for a strong acid with a strong base is hydrogen ion plus hydroxide ion forming water. The equivalence point sits at pH 7 because a strong acid neutralized by a strong base leaves only a neutral salt in water. Now let's solve a couple of practice problems together. This first problem says, what is the pH when 200 milliliters of a 0.1 molar potassium hydroxide is titrated with 100 milliliters of a 0.5 molar hydrobromic acid? Now, to solve this problem and to solve the next one, we're going to be using a Rice table. Specifically, our Rice table is going to be in moles for both because the volume changes during a titration, and moles lets us handle the 1-to-1 neutralization cleanly. For strong acid, strong base, we always reduce the chemistry to the same net ionic reaction. Hydrogen ions plus hydroxide ions gives us water, and all of the spectator ions are ignored. So for this first problem, we're going to begin by drawing up our Rice table. So in the reaction line, we write our net ionic equation. H plus OH minus gives us water H2O. Next, we're going to translate each solution to moles before mixing. So potassium hydroxide is a strong base. It's going to supply hydroxide. Its molarity is 0.1, which means 0.1 mole per liter. To convert this to just moles, we are going to multiply it by the volume, which is 200 milliliters or 0.2 liters. When we multiply that out, we get 0.020 moles of hydroxide ions. HBr, this is a strong acid, so it supplies hydronium ions, or we're going to write H plus hydrogen ions. To get the moles of hydrogen ions, we're going to do the same process. Its moles are the molarity, which is 0.5 moles per liter, multiplied by the volume, which is 100 milliliters. That is 0.1 liters. The multiplication of that gives us 0.05 moles of hydrogen ions. So initially, we have 0.05 moles of hydrogen ions and 0.02 moles of hydroxide ions. The reaction, it consumes them in a 1-to-1 ratio. So the limiting reagent here is going to be the hydroxide ions because we have less moles of them. All 0.02 moles of hydroxide ions are used up, and exactly 0.02 moles of hydrogen ions are used up with them. So we add that into our change line. Then at the equilibrium line, it's going to be initial plus change. So we therefore are going to have at the equilibrium line 0.03 moles of hydrogen ions remaining and 0 moles of hydroxide ions remaining. We turn that leftover into a concentration by dividing by the total mixed volume. The combined volume is 200 milliliters plus 100 milliliters, which is equal to 300 milliliters. We want to convert that to liters. It's equal to 0.3 liters. Then we can calculate the hydrogen ion concentration as 0.03 moles divided by 0.3 liters, and that is equal to 0.1 molar. The pH is then the negative log of the hydrogen ion concentration. So the negative log of 0.1, that is equal to 1. That matches the intuition. We had more strong acid than strong base, so the solution is strongly acidic. The second problem asks us, what is the pH when 100 milliliters of 1 molar HClO4 is titrated with 900 milliliters of 0.1 molar NaOH, sodium hydroxide? Same idea here. Perchloric acid is a strong acid, so it contributes hydrogen ions. Its molarity is 1, so to find the number of moles, we take 1 mole per liter, and we multiply that by the volume, which is 0.1 liters. And that gets us 0.1 moles of hydrogen ions. Sodium hydroxide is a strong base, so it contributes hydroxide ions. And through a similar process, we can find the moles for hydroxide ions. The number of moles is equal to the molarity, 0.1 mole per liter, multiplied by the volume, which is 0.9 liters. And that gives us 0.09 moles of hydroxide ions. So initially, we have 0.1 moles of hydrogen ions and 0.09 moles of hydroxide ions. They react in a 1-to-1 stoichiometry, so the limiting reagent is the hydroxide ions again. All of the 0.09 moles of hydroxide ions are consumed along with 0.09 moles of hydrogen ions. Then at the equilibrium line, we're going to be left with 0.01 moles of hydrogen ions and 0 moles of hydroxide ions. Next, we're going to want to convert to concentration using the total volume, which is 100 milliliters plus 900 milliliters. That's a total of 1,000 milliliters or 1 liter. That gives us that the hydrogen ion concentration is equal to 0.01 moles divided by 1 liter, and that is equal to 0.01 molar. Finally, we can calculate the pH. The pH is equal to the negative log of 0.01, and that is equal to 2. That also checks out conceptually. A slight excess of strong acid should leave us acidic near pH 2. So both problems here boil down to the same narrative. You want to write the net ionic equation. Hydrogen ion plus hydroxide ion gives us water. You want to convert each solution to moles and use the one-to-one stoichiometry to find which reagent is left at the equilibrium line. Then you're going to divide by the total volume to get a concentration, and then you can finish with calculating the pH or pOH depending on what you're asked for. Next up, we're going to move into the second titration type, a strong acid titrated into a weak base. So let's think strong acid like hydrochloric acid from the burette reacting with a weak base B in the flask like ammonia. We're going to read the curve from left to right. Again, the vertical axis is pH. The horizontal axis is the cumulative volume of strong acid that you have delivered. We're going to start at the initial pH of the weak base before any acid is added. Because only the weak base B is present, the solution is basic and the pH is above 7. As soon as we begin adding strong acid, we create a buffer in the flask. The reaction of a hydrogen ion with the base converts some of the base into its conjugate acid, written as BH with a +1 charge. So for a stretch of the titration, we have both the base B and the conjugate acid BH plus present together. That pairing of a weak base plus its conjugate acid is exactly what a buffer is. In the plot, it shows this gentle sloping, nearly flat buffer region because added acid is being soaked up by the conjugate pair rather than going into effect in swinging the pH wildly. So in this buffer region, the Henderson-Hasselbalch relationship is going to be our best tool for calculating anything of interest. In addition, inside that buffer region, there is an important landmark. That is the half equivalence point. This occurs when you have added exactly half the volume of strong acid required to reach the equivalence point. Looking at the stoichiometry, that means you have converted half of the original base into the conjugate acid. So the concentration of base and conjugate acid are going to be equal. When a buffer has equal concentrations of the base and the conjugate acid, then the Henderson-Hasselbalch relationship, it collapses to a simple identity. The pH is equal to the pKa of the conjugate acid. At 25 degrees Celsius, you can also write the pKa of the conjugate acid is equal to 14 minus the pKb of the base. This half equivalence shortcut is a great way to read pKa straight from the titration curve. Then as you keep adding acid, you're going to arrive at the equivalence point, which is shown by the black dot on the plot here, where the curve takes its steepest drop. Chemically, every mole of the original weak base has now been converted into the conjugate acid, so there's no weak base left. The solution at equivalence is therefore a solution of the weak acid BH+, and it partially donates protons to water. Because the species present is an acid, the pH at equivalence is less than 7. If you want to compute it, we would treat the weak acid, the BH+, as a weak acid, where Ka is equal to Kw divided by Kb. And we would use the usual weak acid approximation, where we can say that the concentration of hydrogen ions is equal to the square root of Ka multiplied by the concentration of BH+. After you pass the equivalence point, then the strong acid in the burette is now in excess. So that excess hydrogen ion controls the pH. So the right-hand tail of the curve, it levels off at low pH. 2 key takeaway points for this section. First, strong acid weak base titrations always have acidic equivalence points because the only active solute at equivalence is the conjugate acid. Second, the buffer capacity, which is how much strong acid you can add before the pH starts changing rapidly. It's going to be the largest when the buffer components are both present in sizable comparable amounts. And it's going to peak right around the half equivalence point where the concentration of your weak base is equal to the concentration of your conjugate acid. On the note of buffer capacity, I really want to make sure we're on the same page about this because it is important. So before we move on to the other titration curves we're going to explore, let's talk about it a little bit more and then tackle a related practice problem together. Buffer capacity is simply how many moles of strong acid or strong base a buffer can take on before the pH starts to swing. There's always a sweet spot for buffers. It works best when there are comparable amounts of the conjugate pair, roughly when the ratio sits between 0.1 and 10. And by the Henderson-Hasselbalch relationship, that corresponds to pH within about pKa of plus to minus 1. Inside that window, the pH moves gently as you add acid or base. But once you push past it and one component is nearly gone, then small additions cause big pH jumps and the buffer is effectively spent. Now, to the question, this is going to really help us solidify our understanding of buffers and buffer capacity. A buffer is prepared from 100 milliliters of 0.1 molar formic acid and 200 milliliters of 0.1 molar sodium formate. Then 0.015 moles of HCl are added. Will the mixture still behave as a buffer? First, we're going to identify the species we have. Formic acid is a weak acid, and formate, HCOO with a -1 charge, this comes from the soluble salt. It is the conjugate base of formic acid. So having both in the same beaker is the definition of a buffer. Next, we want to count the moles that are present before any hydrochloric acid is added. So we're going to calculate moles by taking molarity and multiplying by volume, with volume being in liters. So for formic acid, we have 0.1 moles per liter. We're going to multiply that by the volume, which is 0.1 liters. That gets us 0.01 moles. Now for formate, we have 0.1 moles per liter. We're going to multiply that by the volume, 0.2 liters, and that gets us 0.02 moles. So initially, the acid-base inventory is 0.01 mole of acid and 0.02 mole of base. So that means that the base to acid ratio is equal to 2. Now we're going to account for the strong acid that we will add. The hydronium from hydrochloric acid, it reacts completely with the conjugate base. Every mole of hydrogen ion removes 1 mole of formate and turns it into formic acid. You add 0.015 mole of hydrogen ions, so that means it consumes 0.015 mole of formate and creates 0.015 mole of new formic acid. So with these changes, we're going to update the total after moles once the reaction has finished. So the formate remaining is equal to 0.02 minus 0.015, which is equal to 0.005 moles. The formic acid present is equal to 0.01 plus 0.015, which is equal to 0.025 moles. Both members of the conjugate pair are still present. So by definition, the solution is still a buffer. Now here's a follow-up. How close are we to the edge? On the acid absorbing side, the maximum the buffer could take was the initial moles of conjugate base, 0.02 mole. We used 0.015 mole of that, which is 75% of its acid capacity. So the buffer is still working, but there isn't much base left to soak up more strong acid if we were to add it. It also helps to check whether we're still in the effective operating window. After the addition, the base acid ratio is 0.005 to 0.025, which is equal to 0.2. That sits comfortably between 0.1 and 10, which corresponds via the Henderson-Hasselbalch relationship to pH within about a pKa of plus to minus 1. So in other words, the buffer action is still effective. If you want a quick feel for the pH shift, here's how you can do that. So again, the initial acid base to acid ratio, that was equal to 2. So pH is equal to pKa plus the log of 2, which is equal to pKa plus 0.3. Afterwards, the base to acid ratio was 0.2. So pH is equal to the pKa plus the log of 0.2. That's equal to pKa minus 0.7. That drop is roughly 1 pH unit, which is noticeable, but it's still inside the normal buffering range. So the final verdict is yes, the buffer survives the 0.015 moles of hydrochloric acid we add. You end up with 0.005 moles of formate and 0.025 moles of formic acid, so the conjugate pair remains. The solution is, however, much closer to exhausting its ability to neutralize any additional strong acid. Now we're going to turn to the titration of a weak acid with a strong base. For this, let's picture a weak monoprotic acid, written as HA in the flask, and then a strong base like sodium hydroxide in the burette. Again, on our graph, pH is on the y-axis, and the cumulative volume of strong base delivered, that's on the x-axis. At the very beginning, the solution is acidic because we only have the weak acid present. But as base is added, each drop consumes the weak acid HA, and it creates its conjugate base, A with a -1 charge. So the solution becomes a buffer mixture of HA and A minus 1. That flat, gently rising shoulder you see at low volumes, that is the buffer region. And while we are in that region, the Henderson-Hasselbalch relationship is our best tool. pH equals pKa plus the log of the mole ratio A-1 to HA. Exactly halfway to equivalence, the moles of HA and A-1 are equal, so that log term is 0 and pH equals pKa. That half equivalence point is both a conceptual landmark and a quick way to read pKa from a titration curve. Then as we approach equivalence, the curve steepens because most of the weak acid has now been converted to the conjugate base. At the equivalence point, all of the initial weak acid has been neutralized, stoichiometrically speaking, by the strong base. So the beaker now contains the conjugate base in water. Since A-1 is a base, the equivalent solution is basic, and the pH at the middle of that vertical rise is going to be above 7. Beyond equivalence, the solution is going to be controlled by the excess strong base, and the curve, it levels off at a high pH plateau. So the takeaways for a weak acid with a strong base are simple. There is a buffer region before equivalence. pH equals pKa at the half equivalence point, and the equivalence point itself is basic because only the conjugate base is active there. The net ionic chemistry that you are tracking the whole time is HA reacting with hydroxide ions to form the conjugate base in liquid water. Finally, let's talk about weak acid and weak bases. When both partners are weak, neither one fully dissociates, so the reaction does not go cleanly to completion. Where the equilibrium sits, and therefore the pH, really depends on the relative strengths, Ka for the acid, Kb for the base. If Ka is larger than Kb, the mixture leans acidic. If Kb is larger than Ka, it leans basic. If they're comparable, it can land near neutral. But there isn't a single universal shortcut here. This case is harder to simplify than the others. And again, we won't work with it much in general chemistry beyond recognizing the setup and knowing that you would need additional equilibrium data to compute an exact pH. We have now seen the various acid-base pairs behave on titration curves. So before we go ahead and tackle examples, I want to give you a clear, repeatable way to solve any neutralization problem that involves at least one strong partner. So the first step for any of this is to begin by stating what you have and classifying each substance as strong or weak. Strong acids and bases dissociate completely in water. Weak acids and bases establish an equilibrium with water. Then we can move into step 2. Decide whether you have a neutralization reaction. If at least one partner is strong, then you can treat that mixture as a neutralization reaction. And that leads us into step 3. Write the net ionic chemistry that actually occurs. If you have a strong acid with strong base, the net ionic equation is hydrogen ion plus hydroxide ion gets us water. This is what you would write in your reaction row in your Rice table. If you have a strong acid with a weak base, there are 2 categories here. If the weak base is neutral, you can write the net ionic equation as hydrogen ion plus base B. That gives us the conjugate acid, BH with a +1 charge. So then you can write that, or the net ionic equation of that, in your reaction row of the Rice table. If the weak base is an anion, then you can write the net ionic equation H plus the conjugate base A with a -1 charge. That gives us a weak acid HA. And you can write that in your reaction row of your Rice table. If you have a weak acid with strong base, then the reaction you can write in your R row of your rice table is HA plus hydroxide ion gives us the conjugate base A with a -1 charge plus water. Then you're ready to move into step 4, which is all about setting up your rice table. Reaction, initial, change, and equilibrium. From step 3, you've already written the net ionic equation in the reaction row. We are then going to set this up in moles for initial, change, and equilibrium. How do we do this? We're going to start by converting each solution to moles. We can do that by multiplying the molarity times the volume. Make sure volume is in liters. And then you're going to place those values on the initial line. On the change line, you're going to decide how far the reaction can go by identifying the limiting reactant. So here you just compare the moles required by the stoichiometric ratio. So for the 1-to-1 neutralizations we are doing, it's simply the smaller mole amount. You're going to subtract that amount from each reacting species, and then you're going to add it to the product side when appropriate. Then you're going to read the leftovers on the equilibrium line. Those are the moles that remain after neutralization. Because we did everything in moles, you can now convert any leftover acid or base to a concentration very cleanly by dividing by the total mixed volume at the end. This avoids the mess that comes from the volume changing during a titration. In step 5, you're going to decide what kind of solution you have after the reaction and pick the right follow-up calculation. So if a strong reagent is left over, the excess sets the pH or pOH directly. If you are exactly at equivalence for a strong acid with strong base reaction, the solution is going to be a neutral salt and water, and the pH is approximately 7 at 25 degrees Celsius. If you are at equivalence for weak acid with strong base, only the conjugate base remains active, so the solution is basic. If you're at equivalence for strong acid with weak base, only the conjugate acid remains active, so the solution is acidic. If both members of a conjugate pair remain, then you are in a buffer region, and here you're going to use the Henderson-Hasselbalch equation to calculate any desired values. And that idea kind of leads us to step 6, where you're going to finish by converting to the quantity that the question asks for. That can be pH, pOH, the concentration of hydrogen ions, or the concentration of hydroxide ions, or whatever else. And you're going to check that your answer makes chemical sense. If acid was in excess, then the pH should be below 7. If the base was in excess, the pH should be above 7. If you landed in a buffer region, the pH should sit near pKa and move smoothly, not make any drastic jumps in that region. Keeping that in mind, we're going to put it into effect by tackling about 4 practice problems. So it's totally okay if these steps don't make 100% sense right now. They are going to make a lot more sense when we apply them to different sorts of problems. This first problem asks, what is the pH when 50 milliliters of a 0.01 molar hydroiodic acid is added to 100 milliliters of a 0.1 molar sodium formate? For formic acid, the Ka is equal to 10 to the negative 4. Let's answer this problem by going through our steps. Always follow the steps. Step 1, we're going to classify what we have. Hydroiodic acid is a strong acid. In water, it produces hydronium ions, or in other words, we're going to write hydrogen ions in the net ionic equation. Sodium formate is a soluble salt, and its active species is formate, HCOO with a negative 1 charge. This is the conjugate base of the weak acid, formic acid. Step 2, we're going to decide if this is a neutralization reaction. The answer is yes, because at least one species here is strong. That is our hydroiodic acid. It's a strong acid. So we treat the mixing as a neutralization reaction. Then we go to step 3. In step 3, we write the net ionic equation. Strong acid with a weak base anion follows H plus, the hydrogen ions plus, the conjugate base, A minus 1. That gives us a weak acid, HA. So here, if we were to be specific, we would write the hydrogen ions plus formate gives us formic acid. Then we'll move into step 4. We're going to set up the rice table here, specifically in moles. So that means we want to convert each solution to moles by multiplying the molarity with the volume in liters. And we're going to take those values and place them in the initial line of our rice table. So the initial moles of hydrogen ions, that's going to be equal to 0.01 mole per liter times 0.05 liters. That gets us 5 times 10 to the negative 4 moles of hydrogen ions. We're going to do the same thing with formate. We have 0.1 moles per liter times 0.1 liter. This gives us 1 times 10 to the negative 2 moles of formate. The reaction, it's going to be 1-to-1. So the limiting reagent is going to be the one that has a smaller amount of moles to start off with. That is clearly the hydrogen ions. So in our change, we're going to consume all of the moles of hydrogen ions, all 5 times 10 to the negative 4 moles. And the same amount will be consumed of our formate. So that means we're going to place that minus change in the change line. Then our equilibrium moles, what does that look like? For the hydrogen ions, it's going to be equal to 0. For our formate, it's going to be 1 times 10 to the negative 2 moles minus 5 times 10 to the negative 4 moles. This gets us 9.5 times 10 to the negative 3 moles. So, because we have consumed all our hydrogen ions, what we're going to be left with for our formate is 9.5 times 10 to the negative 3 moles. What do we create? Right? We have formic acid as our product. That means in our change line, we need to account for creating the same number of moles that we have consumed in the reactant side. So we have 5 times 10 to the negative moles of formic acid in the change line. Then when we come to the equilibrium part for our formic acid, we had 0 to start off with. We form 5 times 10 to the negative 4 moles. We are going to end off with 5 times 10 to the negative 4 moles of formic acid. Because volume changed during mixing, we're going to convert to concentrations only after we decide what calculation is needed. So that allows us to move into step 5. We need to identify the post-reaction solution and choose the appropriate follow-up calculations. Now, both members of the conjugate pair are present. What you notice in our equilibrium line, we have some concentration, or let's say we have some number of moles of formic acid and formate. So we are in a buffer region. Here we're going to use the Henderson-Hasselbalch with mole counts for us to make any calculations. So we're going to set up pH equals pKa plus the log of base divided by acid. This is equal to pKa, which is 4, plus the log of 9.50 times 10 to the negative 3 divided by 5 times 10 to the negative 4. This is equal to 4 plus 1.28. That is equal to 5.28. So step 4, we're going to report the requested quantity, which is pH. We just calculated pH is equal to 5.28. Let's think about this. Is this reasonable? It is in fact reasonable. We added strong acid to a formate solution and we ended up with a buffer with pKa equal to 4 and an base acid ratio that's equal to approximately 19. The pH should be a bit more than 1 unit above pKa and still below 7 pH. And that's exactly what we found. Let's go ahead and tackle the second problem. The second problem says, what is the pH when 100 milliliters of a 0.1 molar lithium hydroxide is added to 200 milliliters of 0.1 molar formic acid with a pKa value equal to 4? Step 1, we want to classify what we have. Lithium hydroxide is a strong base and formic acid is a weak acid. Step 2, we want to decide if this is a neutralization reaction. The answer is yes, because there's a strong acid that's present. So we're going to treat this as a neutralization. Step 3, we're going to write the net ionic equation. This is a weak acid with a strong base, so it follows HA plus hydroxide ions gives us the conjugate base plus water. Step 4, we want to set up the Rice table in moles. So the initial moles of hydroxide ions, we can calculate this by taking the molarity, 0.1 moles per liter, multiply that by the volume, 0.1 liters. This gives us 0.01 moles. What about the initial moles of the weak acid? We have the molarity, 0.1 moles per liter. We multiply that by the volume, 0.2 liters, to get 0.02 moles. The reaction is going to consume completely the smaller amount, which is the moles of hydroxide ions, and this happens in a 1-to-1 ratio. So in the change line, for the reactants, we're going to lose 0.01 moles of both the hydroxide ions and the weak acid. And what we form ultimately is 0.01 moles of the conjugate base. What are the equilibrium moles then? Well, for hydroxide, it will be 0. For the weak acid, it's going to be 0.02 minus 0.01 moles. That is equal to 0.01 moles. And then for the conjugate base we form, that is just going to be equal to 0.01 moles. Next up, we have step 5. We need to identify the post-reaction solution and then choose the follow-up calculations we need to do. What we're left with, you'll notice, is equal moles of both the weak acid and the conjugate base. That is the half equivalence point of a weak acid strong base titration. So the Henderson-Hasselbalch relation, it collapses to pH is equal to pKa, which is equal to 4. Our final step is to report the requested quantity and do a quick sanity check. The result is pretty consistent with the theory we covered earlier at half equivalence. For a weak acid conjugate base pair, the pH equals to pKa. We can now move into the third problem. The third problem states, what is the pH when 80 milliliters of 0.125 molar hydroiodic acid is added to 20 milliliters of 0.5 molar sodium formate? For formic acid, the Ka is equal to 10 to the negative 4. Again with our steps. Step 1, classify each substance. Hydroiodic acid is a strong acid. Sodium formate is a soluble salt whose active species is formate, the conjugate base of the weak acid formic acid. Step 2, we want to decide if this is a neutralization reaction. Yes, because there is a strong partner present. So we can treat the mixing as a neutralization. Step 3, we write the net ionic equation. Strong acid with a weak base anion is written as H plus A minus 1, right? The conjugate base. That gives us weak acid HA. Now we move into step 4. We set the rice table up in moles, which requires us to convert each solution to moles. The initial moles for hydrogen ions, it's going to be equal to the molarity of the hydroiodic acid, 0.125 moles per liter, multiplied by the volume, which is 0.08 liters. That gets us 0.01 moles of hydrogen ions. Then we're going to do the same thing for forming. 0.5 moles per liter times the volume, 0.02 liters. That gets us 0.01 moles. They're going to react in a one-to-one stoichiometry. And guess what? They're present in equal amounts. They both have the same number of moles. So both of these species, they're going to get completely consumed. The product formed is going to be 0.01 moles of formic acid. So in that change line, we subtract 0.01 moles for both hydrogen ions and for formate, and we make, so plus 0.01 moles for the weak acid, formic acid. And you'll notice in the equilibrium line, both reactant species are equal to 0, and the product formed is 0.01 mole formic acid. The total volume after mixing is going to be 0.08 plus 0.02 liters. That gives us a total of 0.1 liters. So the resulting formic acid concentration is going to be 0.01 moles divided by 0.1 liters. That is equal to 0.1 molar. Step 5. We got to identify the solution and choose the follow-up calculations. So at this point, the beaker only contains a weak acid. So we're going to treat this as a weak acid solution. To calculate the concentration of hydrogen ions, that is just going to be equal to the square root of Ka multiplied by C sub A. So the concentration of the weak acid. Ka is equal to 10 to the negative 4. That's the Ka of formic acid. That's what the problem gives to us. We just also calculated the concentration of formic acid as 0.1 molar. We multiply those together. That's equal to 10 to the negative 5. We got to take the square root of that. So the square root of 10 to the negative 5, that's going to be equal to 10 to the negative 2.5. Now we can move into step 6 where we finish the calculation and do a quick sanity check. pH is equal to the negative log of the hydrogen ion concentration. We just said that the hydrogen ion concentration is equal to 10 to the negative 2.5. So pH is going to be the negative log of that number. pH is equal to 2.5. That makes sense. At the stoichiometric point, for a strong acid plus conjugate base, only the weak acid remains. So the solution should be acidic, and that is exactly what we calculated. Now we can move into our last and final problem. This one says, which of the following statements is true about the titration of 200 milliliters of 0.2 molar ammonia? It has a Kb equal to 10 to the negative 5. With 100 milliliters of 0.4 molar chloric acid. Step 1, we want to classify each substance. Ammonia is a weak base. Chloric acid is a strong acid. Step 2, we're going to decide if this is a neutralization reaction. The answer is yes, because there is a strong acid present. Step 3, we're going to write the net ionic equation. For a strong acid with a neutral weak base, we can write hydrogen ions plus the weak base B gives us the conjugate acid BH plus 1. Step 4, we're going to write the rice table in moles. So here we need to do a couple of conversions to figure out the number of moles of our weak base ammonia. We're going to take the molarity and multiply by the volume. So this is 0.2 moles per liter times 0.2 liters. And that gives us 0.04 moles. We're going to do the same thing with our hydrogen ion concentration. We take the molarity, multiply by the volume, 0.4 moles per liter times 0.1 liters. And that is equal to 0.04 moles. Now, they're equal. And guess what? They react in a 1-to-1 ratio. So that means we're going to consume both these species in the process of forming our conjugate acid. So we write in our change line for both the weak base and the hydrogen ion concentration minus 0.04 moles. And for our change in the conjugate acid, since we're forming it, we write plus 0.04 moles. In our equilibrium line, we have 0 moles of our hydrogen ion concentration and our starting weak base. And we have 0.04 moles that we formed of our conjugate acid. We can take that and then we can divide by the total volume, which is 0.3 liters, to get the concentration of our conjugate acid, which is essentially ammonia. That is equal to 0.133 molar. Now we can move into step 5. At equivalence for a strong acid plus a weak base, the beaker is only going to contain that weak acid, so ammonium only. Therefore, the pH at equivalence is going to be below 7. If we want to do a quick check, we can calculate this. We can take Ka of ammonium. That is going to be equal to Kw divided by Kb. We have both of those values, so we can plug them in. 10 to the negative 14 divided by 10 to the negative 5. That gives us the Ka of ammonium, which is the conjugate acid. That is equal to 10 to the negative 9. Then we can calculate the hydrogen ion concentration by doing the square root of Ka multiplied by C sub A. We have both of those values, so we can plug them in. Ka is 10 to the negative 9. C sub A is 0.133 molar. The hydrogen ion concentration is going to be equal to 1.2 times 10 to the negative 5. Then we can get the pH by taking the negative log of 1.2 times 10 to the negative 5, and we get a pH value of 4.9. For step 6, we finish up and we do a sanity check. Everything is consistent with this well-known pattern. Strong acid, weak base titrations are going to have acidic equivalence points. Therefore, the correct answer here is B. This is a titration to the equivalence point, so pH is less than 7. And with that, we've completed this lecture. I hope it helps. Good luck, happy studying, and have a beautiful, beautiful day.